Good morning. My name is Kent Milfeld, and I'm from the Texas Advanced Computing Center, just up the road a piece. And I'd like to thank Intel for having me here to present some of the new directives that are available in the Intel compiler. And what I want to get across to you is that these new features are available, and it's a good time to move on to using these features in the Intel compiler. So what I specifically want to go over is the offloading directives and the Simdi directives. Now, Intel now has in the in the 16 version of their compiler, they have OpenMP versions of doing the offloading. They're ones they initially came out with are called Leo offloading, meaning language extension for offloading. Those are Intel directives specific to their compiler. And then in the Silk Plus, they have the Simdi directives. So what I want to do is talk about those, how to convert over to using those, and how easy it is. And for the experienced OpenMP users, you'll see some of the differences, some of the limitations, and a little bit of the additional features. And for those who are new to using OpenMP, you'll see how it works and that you should start using these, and they are now available. And I just want to point out that the language committee, the OpenMP language committee is very active in finding out what the vendors are doing and then putting that into the standard across lots of different compilers. The GNU, IBM, Cray, and NVIDIA, they're all present at the committee meetings. They meet once a week. They have subcommittee meetings also once a week, so it's not uncommon for people to twice a week join these meetings and work on the OpenMP standard. And OpenMP is not specific to the platform like the Leo directives or the Silk. It's across different types of platforms. These subcommittees are very agile. It doesn't take years to get these new directives into the standard. And the good thing is that it can be used on different platforms. So just a little bit of history about OpenMP. Of course, it started out with threading and then moved on to doing task, and we could do task loops now, something that's fairly new. And then presently, they've come up with doing thread affinity, so you can express that in a generic way. There's also task dependencies available now, so you can do dependency graphs in terms of executing different tasks. And the things I want to discuss today are the offloading directives and the Simdi directives. And then, of course, in the future, the committee's already discussing having directives that specify memory locality and NUMA and memory hierarchy. So which type of memory you would want to use for something. So they're moving on, and that's good. So first, outline for the offloading, and I have another outline for the Simdi. When we get to that section, I want to go over some of the basics so you have a good feel about what happens in offloading, and then discuss data movement and persistence and concurrency. For those people who are here listening to the H streams in the session before, it's basically what was talked about in CJ's discussions. And so we'll go through that and then look at, I have a page, an eye chart, that shows you a comparison of how to go over from the Leo directives, language extension for offload, the Intel, over to the OpenMP. And that's what I want to show in this first half of this session. So the basics for doing offloading, we think about having a couple processors in a node, having a PCI Express bus connected to a device, and when you want to do offload, you simply have a block of code that you say specify with a directive that's to be executed over on the device over here, and that's good. But the important thing is that the people want to do is do things asynchronously, or concurrently, and so you'd want to have executions over on the host while executing something over on the mic that you pushed over there through an offload statement. So the important aspects about that are the data transfer and the allocation and the concurrency. So we all know that you want to minimize the amount of data you transfer over there, that cost, but also people don't realize that there's a considerable cost in allocating that memory. You might push over, say, 6 gigabytes over there. It would take a second because you have a PCI Express about that time, but it may even take much longer than that, maybe 2 or 3 seconds to take care of the allocation over there. And so one of the important things is to have persistence of data over there. If you have a space over there, you reuse it, you transfer over to it. Each time you do an offload, you don't want to allocate the space and then use it and then have another offload, free it previously and then allocate it and then free it. You don't want to go through that process. You want to have things persistent over there. And so in any offload step, you are going to be detecting whether the mic is over there. You're going to be allocating the memory over on the device, transferring those variables that you had on the host over there, then executing it. So offloading is not just about execution, it's about these other things too, persistence of data, the transfer, and the concurrency over there. And both the Intel and the OpenMP directives, you can do this, very simple things you can do with a simple directive, but when you want to be efficient about it, you have to put on these clauses to that directive to say how you want to do things. And for example, just an elementary offload, you have a block of code here, C code. That's all you have to do is state that this is to be offload over to a device, and under the covers, space was allocated on the device for A and B. Those were both transferred, whatever the values were on the host over there. Then the operations were executed over there, and then data is moved back, and then it is going to be freed. That space is going to be freed. So all those things are occurring. It's, you have to specify that it's going to be on a mic here, so it's offload target mic. On the OpenMP side, the expression is OMP target, and then you specify a device. If you have multiple devices, of course, it's going to be important, but in the OpenMP, there's a default device, and you don't even have to put that on there. So it's just OpenMP target for this block of code. The compiler sees what it needs over there and does some of these things automatically in the background. Now, if you want to be more efficient, if you have a code that does something like this, where that's all I do is assign to A, and that's all I do is read B, and then maybe use C on both sides as a read and a write, it's obvious that I don't need to, that I need B over there, but I don't need to bring it back because it's only read. So I can specify and be efficient. Of course, here I just show a variable, but these can be arrays. I show that we can do specify an in or an out for A and B, and so it's only going to go one way, the transfer, and or an in-out saying I want it moved over there in the beginning and then brought back. In OpenMP, that's done with the map to, the map from, and the map to from. So it's a little bit longer expression, but it does basically the same thing that the Intel does. So you can do the same thing there. So basically the automatic stuff's the same. The expressions for moving on and offload directive, moving data in a particular directions are both over there, so that's good too. The other thing is that you want to have persistence over there, and so we're going to look at the directives for doing that. So we might allocate space, do an offload, do some sort of transfers to that allocated space, and then maybe have another offload and then do some transfers after that. And deallocate explicitly outside of doing that particular offload, using those directives, those specific offload directives. So on the Intel side, on the Leo side, they initially came out with what we call the unstructured way of doing that. That at any point I can allocate that space over on the device within the code. Any place within the code, I can allocate the space. I can transfer things over there or bring them back, and I can also deallocate it. That's called unstructured. The OpenMP standard, the 4.0, only came out with what we call a structured directive. You make a block around any particular areas where you're doing your offload, and then you specify at the top how you want the data transferred and how you want the allocation to go. And we're going to go see an example of this, as well as the OpenMP 4.5. Actually, yeah, people are saying the next standard, well, we have 4.0 OpenMP. They're officially calling it OpenMP 4.5, the one they're going to release this week. So I refer to it as 4.5, not 4.1. Okay, so this is how you do it with the Intel directive. You would have a transfer directive, and then you would have options on clauses on that line to talk about what you want to do with various variables. As we saw before, you can say whether you want it transferred over there, transferred just back, or if you're going to do a no copy, and you would specify, and you would specify if you want it allocated or not. And the way you read this clause in here is to say, if this variable is true, which can be expression, I want that space allocated. And if this expression is true, I want it to be freed. So if I want to allocate the space and transfer something in, I say in here, and I make this true, and if I want it to be persistent, I say don't deallocate it. So you're specifying data motion, both data motion and how you want the allocation and or freeing to occur in this directive here. It looks very complicated, but you get very used to it. You say, I want to push data over there, that's going to be in. Or if I just want to bring data back, I want to be out. And usually you transfer data in, you allocate the space, and you say, don't free it right now. I just want it allocated. Bringing it out, and if I want to free it, I make this, I use this in the expression, and I say, I don't want you to allocate it because it's already been allocated, but I want you to free it after you bring it out. Or not. If you just wanted to get the data over, then you say don't free it or don't allocate it, both those expressions. People make macros for these, so they say reuse or free or allocate, and that makes life a little bit easier. But basically, any place within the code, you can tell the compiler that you want to move data over there and how you want the space allocated or not. You can also do this on the offload statement itself. On the offload, we saw how we could push data out, push data just in, or just make it come back at the end of the execution. These two operations here, this work at the beginning of the offload or at the end of the offload. So at the beginning, I may want to allocate space and not free it at the end, and I could want to move the data in or out, and you could also use no copy down here. Okay, so that seems very, first time you see that, that's pretty complicated. OpenMP, the reason people really like the structured way of doing it because it's a lot simpler. You have operations in here, certain types of offloads, and you would simply make data persistent by saying target data. You don't even have to include device, and you'd say how you want it mapped there, and that is at the beginning of this block, if you put a 2 there, it's going to copy it over. If you put a from for this variable over here, or set of variables, then it's going to copy it back, and the default here is actually a to from, which says it's going to allocate the space, it's going to persist, and at the beginning I'm going to copy things over, and at the end I'm going to copy them back. And you can have updates in here at various times to update those persistent variables. So it looks a lot cleaner in the OpenMP, and it's actually a little bit different because it's structured. But if you do need this fine granularity of moving data back and forth, and in particular about allocating that space, the 4.5 standard has this available, and Intel in their 16 compiler has this available now. So Intel has been very aggressive about keeping their compilers up with the latest and greatest. Then this week they're announcing the 4.5, and actually it's in the standard right now. So that's pretty good. They're very aggressive about that. So the way you do it with the OpenMP is you specify that you have an enter, meaning I'm going to move data or enter data over into the device, or I'm going to exit it and bring it back over. So there are two different directives in terms of which way you're moving data, and you have a map that you could say, I want it to, and if you say to, it's going to allocate it. And if you're not going to move any data over there, you can simply say target, enter data, map, alloc, and the variable names there. And that's how you create a persistent variable or set of variables over on the mic. Likewise, with bringing them back, you can specify they're going to be from, which will remove it, or you can say that you want to delete that space. Here's an example. Let's see, can you read? Yep, that's readable somewhat, I guess, for the people up front. And so here's how we would do this with the Leo up here. We create these, and there's one important point I want to bring out in this comparison. I create some variables up here, and on the Intel side, I say I want to do a transfer, and I'm going to, this is true, so I'm going to allocate the space for C over there at this point up here. So I'm going to make C persistent. Down here, I'm going to remove it because I'm going to do a free on that, and I'm going to copy it out. So up here, I'm going to make it persistent. I'm going to copy it over there. Here, I'm going to bring it back. I do the same thing over here in the OpenMP with an enter and a map C, and by default, that will move it to. Okay, and then back here, I'm going to do the exit, which brings it back and call map. This is a little bit cleaner, the OpenMP way of doing it. Yes? Is there what? Oh, for functions? No, this is just for transferring data over. Yeah, but not a function.
Yeah, but for instance, if I want to transfer data to the device in function A, exit function A, and then want to reuse it in function C or so.
Yeah, you could do that.
Okay.
Yeah. Okay.
The enter and the exit don't have to be in the same lexical scope.
Yes. Yes. Okay. The important difference here is that if I'm over here on doing it with OpenMP, and I say changed on the host, this was copied over there and made persistent. If I change C over on the host, when I execute this code over here, it's not going to know the new value. Okay, you have to explicitly move it over there. On the other side over here, if this is in the lexical scope, C right here, and you don't have this no copy, it's going to copy this value over there, as well as A and B. It sees that within the scope and it says, I'm going to copy. It'll still be persistent, but it will copy over. So this is one of the learning curves. You have to go, one thing that's important between these two. So if I don't want it copied over there, which is, to me, the usual case, you would put a no copy C here, and it's not going to automatically move this value from here to here. On the OpenMP side, it says, you did something up here, that's persistent. Unless you're explicit about it later on, we're not going to do anything. Only the things, these implicit things down here, which it sees in the scope that it knows nothing about. So that's one big difference that I want to point out in the two. Okay, and so that's basically the things I said. You'll be allocating space up here, and don't free it back here, and you'll push it over. You copy back and free here, and then this is about the things that are happening automatically and C stays persistent. But you have to use this no copy on the Intel side to do that. Now, if you're doing, and this is, I just wanted to show this in terms of how simple it is. If you have something simple where I want to have something persistent at the beginning of this block of code or set of directives, and I want it to come back at the end, then it's simply OpenMP target data, and I map C, and that will be persistent for all my different offloads. Yes?
You do not specify the target, so if you have multiple targets, how does
So up here, if I wanted to do over here on this side, I would just say device 0. It defaults to 0. If I wanted, and I'll show you an example of using 2 devices. Over here, whether you use 0 or not, you can specify the device over here. Whether you specify that or not, you still have to have the target mic. Whereas over here, that's good because if they wanted to change, mic, different types of mic or something, they have this capability right away. OpenMP standard does not have types at this point. It assumes you only have one or two different mics on there, but you can't, I don't think anybody's doing mic offloads at the same time that they're doing GPU offloads. So we do have time to get that into the OpenMP standard at this point. So what about doing things asynchronously? One of the things is to do, when we do things synchronously, when you come to an offload directive, you simply say, go do this offload. The host waits there until the offload is done and then begins executing after that block of code that was offloaded after that. For asynchronous, y'all know what you do want is for the process or the thread that's coming down and doing the offload to let go of that and start executing host code over here. And this is called asynchronous, what we mean by asynchronous offload. And so that you can have concurrent execution of something on the host and then a block of code on the device. And we're going to look at how you're doing that. With Leo, they have what they call the signal clause on an offload statement. And that indicates that it should be run asynchronously, that the thread or the process should continue executing immediately after that. And then later on, when you need to synchronize, you simply use a wait, and you specify a signal ID up here for the offloaded process, and then down here someplace else you do a wait for that. The OpenMP standard provides a no wait option that says we're going to do this asynchronously, and then you do a task wait later on. And there's no explicit task that's being used over here, but the standard says that there is a task in the background that's doing this, and it's not 100% clear about how that is operating, and it's up to the vendor to make that as fast and efficient as the Intel offload.
Since you've added the task here, we don't actually have to create the task in the offload?
Exactly. It is called a target task. And if you read the 4.5 standard, then you immediately ask, is it explicit or not? It's sort of an implicit task. Basically the same thing that's happening here, because something has to be doing it in the background. Some thread has to go after that and execute it in the background. The basic idea, a good implementation will have that thread start the offload and then come down and assist in any other operations that you do on the host. Say if you had 16 threads or cores on the host and you wanted to use 16 threads down here, a good implementation would allow you to do that. Whereas an implementation, I'll show you this, that's not so good, would actually hold on to a task and use that and wait for it to complete, whereas a good implementation will say, hey, I did the offload, signal me when you're ready, I'm going to go down here and work in another team that you're doing executions on the host with, okay? So how does this look like? What does this look like? So in Intel, it's very nice. We have 16 cores on the host. We have a pragma to do our offload up here, and we put the signal. We say we're going to do this asynchronously. This is just an OpenMP directive down here saying what to do over there. Very simple. Down here, I have a pragma for doing a parallel execution. These are identical except for, they do the identical thing. This says do that offload, do this parallel on the device, and this is to be done on the host. Now, when you put the signal up here, the main thread that comes down here immediately says, I'm going to put this in the background, and I'm going to come down here and start executing this. So if you put a clock here and here, you'd see, oh, that took no time at all. It's going to take 2 seconds on the device, though. And while that's running over there, this thread comes down here, forks a parallel region, and boom, it's going to take 2 seconds. And so basically, this was running concurrently over on the device. This was running on the host, and then you do a no wait on the. You do a wait with the standalone directive on the signal ID to synchronize. Okay, and so that's how that works. With the 4.5, you can do a no wait up here and here's your parallel on the host, and then do the task wait down here for synchronization. Okay, so basically you have the same thing operating here. Okay, and that's nice. It's going to work in the background. It's going to do just what you want. Up till the release of the 16 compiler, Intel 16, there was no, they didn't have a no wait in there. The latest release of the 16 compiler has the OpenMP 4.5 no wait in there. So you can change over now if you have that compiler. The way you had to do that before was what I wanted to show here is that somebody was asking about doing 2 different devices. If you have 2 cards on the system, you could do a no wait and you say device 0. You could do a no wait here and tell it I wanted that on to execute on device 1. Now, the problem with the OpenMP version of doing async is that unlike the Intel version, you had an ID, and you could specify another offload here for a different device and specify the ID. With the no wait, you don't have an ID for what's being backgrounded. And so how would you actually do have multiple use multiple devices here? It's not really clear. And the way to do that is going one step beyond and using dependencies, which are new. You can, and it's a sort of like a flow dependency. Here I say, I have a dependency, and this is going to be out on my flow. It's dep 1. And if I have a dependency on some other directive down here, I can declare it to be in on dep 1, meaning this thing has to be done up here before I can start this operation here. And so what I actually do is make a dummy task down here, and I just put dependencies on it. The task doesn't do anything, but it causes it to wait for these 2 processes down here. So basically a master thread comes down here, does a no wait, pushes over to device 0, says, oh, I got a dependency, okay, something else is going to want this, and I have to, and if I do, I'll have a dependency clause, I'll have to work that out. And so it comes here, does that in the background, does this in the background, comes down here, forks 16 threads, does this, comes down here, have something else, and if I need, I do my synchronization with a do nothing task. Yes?
Was
On this one, I think it would abort, but I do not know. I have not tried that.
So code has to know ahead of time whether there's one or two devices.
Those don't have to be constant.
Yeah, yeah. But then it wouldn't be very well balanced too, because then what? Say if it wouldn't be balanced. So of course, on anything you have to worry about how it's going to be balanced. And if you're specifically doing this for two devices, there would be more code that you'd have to put in there if you had if you wanted to back down from to one device if there weren't two. You'd have to discover that and put it out. And there are directives you can use to discover the number of devices. Okay. The other important point on this task is that there's this clause called the if clause, and I would make it so it does not defer it. Lots of times you come to a task, it's throwing things on the task queue and then picking them up at any time, and here it says, no, no, no. You need to not defer this one to do it. Yes?
You said that for the asynchronous offload, there is one additional thread that is more on one of the previous slides.
Yeah. So actually, officially, when you do the no wait, there is a task that is being performed called a target task, not the normal task you hear of. Yes.
In the sample you showed on the last slide, does it not mean that there are two threads that are spawned, or is it one thread that processes both of these?
Oh, for both of these right here?
Yep.
Yes, there'd be two. I would suspect. Yeah.
A task is not the same thing as a thread. Right? So
Yeah.
it's creating tasks, it's not creating threads. Something has to, as asynchronously progress this, which likely means that there's one worker thread somewhere in that the runtime implementation, or the live offload in our case, the runtime implementation doing that.
Yep.
You don't have to have separate progress threads for each different device.
Yeah.
Necessarily. I mean, if you really want to know what it does, go read the code of the offload. It's all out there.
Exact.
You can find it, but so I work on the OpenMP runtime, which is a separate issue from the offload runtime, which turned out to be a very technical decision, although it was actually made more on the basis of the compiler team doing offload and we're doing the other. So it's made through the fact that people reported to different managers rather than anything else. But the
Yeah.
offload stuff is all completely separate from the OpenMP.
I just want to make sure that if I have multiple of these asynchronous offloads,
Yeah.
that there is not
There should not be, and certainly the objective is that you don't get a subscription. The point of really trying to get.
Yeah. Oh, thank you very much. And that's basically what I learned when I actually last summer translated a Lattice Boltzmann code over and found out all these things. And I've never really worked with tasks that much, but the important point is a task is not a thread. A task is something thrown on a queue to be executed by some thread later on. Question?
So, if I was in a situation like this, I probably wouldn't want to specify how many. I'd want to do it programmatically, like what
Right.
was saying.
Yes.
So, is there a way in that last statement to also identify how many that I have in release, yet in that statement to release them all? Or would I have to have a pragma for each one of the releases?
In here, yes,
Right.
because this depends upon both of them. I think it's very specific. I have not looked into not doing that. As a matter of fact, we discussed this and put this slide on here last week. I have not had experiences other than quickly running this to make sure it works, because somebody said, well, what if I have two devices there? And I've only been worried about one, because that's how we run most of our codes up at TACC. And so I thought I'll put that on there. But yes, if you're going to change the number of devices there, this, of course, to do each one of these, you'd have to worry about the data there. So that's very, very specific, and I guess you would have to have this. And so I don't. Oh, good point.
You can have dependencies on array elements. So you can.
Yes. Oh, that's a good point.
So you can do much more here than is needed. It's complicated and horrible in my opinion, but I can have a lot.
That's why I didn't put that up there either.
At the bottom there is programmatic
I
Well, he was
no. Well, one of the things I'm.
that Ray-
Yes, you could write a loop around there, and the first one would actually have to stop, and you'd have, this would be an array here, and you'd come back around. But you could have, I guess you could have array with a variable here. Yeah, you could do that, exactly. Yeah, so you could do that. So, but we're getting into the more complicated stuff that some people don't even want to see. Yeah.
And as I said, I work on the OpenMP runtime, so I try and ignore this stuff to live off like that. But we did have to make sure that the task dependency mechanisms work with these that are in the OpenMP runtime work with these what I prefer to call surrogate tasks. Because they're not tasks on the device, they're tasks on the host that represent progress on the device.
Yes, and it's a good way to put that. Excellent. So this is what you had to do with OpenMP 4.0 up right before the 16 compiler came out. You would have to do something like this. You would have to put your you'd have to put the parallel region around the region here. And the reason is, if you didn't have this parallel region on the outside here, you fork your 16 threads, and if you just came down here with the master thread and did a task, it would put it on a queue and then try and execute it immediately. And so you would have a problem that this wouldn't become asynchronous. You'd have a task, and because you only have one thread to execute what you threw on the task queue, it would execute that. So the best way to do that is to put the parallel region on the outside, which is a mess, which I was so happy when they came out with 4.5 and they had the no task and you could do asynchronous things that way, because I coded up this person's code to do this, and it was a little bit of a mess and a hassle, and I thought we could certainly do it better with OpenMP.
So the critical thing to say about this is you don't have to do this any longer.
Yes, that's
It's unpleasant, but don't worry, it's gone. Makes it much nicer.
Yeah, but it is important and instructive to see how this was done, and that's why I threw it up here. Parallel region on the outside. You generally create a task, but you want other threads around there and some team to be executing what you throw on the task queue. And this is what you see for other methods that just need a lot of tasks out there. The parallel region will be on the outside. They'll have a loop around here to throw these tasks on the queues and start executing them with these other threads out here, but one of them is going to be the generator. And so that's basically what you had here. One generating the task, throwing it on the task queue, and that task queue's one of the other threads picks it up, but it then comes down here and it can make progress and come through here. This task is in the background. This gets executed on the host, and then you do a task wait down here. So that's the old way, but it's instructive to see how this operates if you want to learn how to use task with OpenMP. Okay. So in summary, basically, which I did not show, there are attributes for declaring functions that you want them compiled both for the host and for the device. And then we have our offload statements, which actually tell it to execute something on the device. And then we have the offload transfer, this is for Leo, allocates, moving data, and then synchronization. And the corresponding ones for OpenMP are target, and then you use a declare target for expressing that you want a function compiled for the device. And up here, it's we have this. For moving data, you do a target update, and then for allocating things to be persistent, you would use either the target data or the target enter data or the target exit data. So it's a little bit complicated. You basically do the same things. You have allocs and releases, and in moving things, you have a map to from, and then of course if you're using arrays or dynamic mallocs or pointers with a space behind it, you have to specify the length. That's something I didn't go over here, but it's the same way in both the Leo and the OpenMP, and then down here you have the asynchronous thing. So it's pretty much the same thing. It's straightforward to move over to the OpenMP. Couple little differences in how things are done, and so I suggest that people move in that direction and start using the standard. If you're using the 15 compiler, you are sort of stuck with the 4.0 things, and if you're using the Intel 16 compiler, it has lots of the 4.5 stuff in there already. And this is the Rosetta Stone. It's in Fortran, and it's don't expect anybody to start reading this. I'll put a C version out there on the XPug site later on, but I just didn't have time to go through this. The code that I translated in the summer was Fortran, so I made this table for myself when I was going through that. And these will be available for you to download.
This is useful to you if you already had code in Intel's Leo. If you didn't have code in Intel's Leo, then don't worry about it.
Yes.
Just write OpenMP 4.5 and
Yeah. So go over there and follow some examples. The standard is a little bit hard to read, first time through. So that's what I wanted to provide for you. The next part, I want to just go over some basic Simdi directives that are now available, and I didn't do any performance testing or anything like that. I just want to expose the little bit of the differences, but mainly of how they look basically the same. And so what is Simdi? It's just the vectorization, and for many years vectorization on Intel processors was just 2 double precision long, which most scientists use, and that's hardly a vector. That's like hyper-threading with 2 threads. That's not so much hyper. But these days, since we have 8 wide instructions for doing floating point operations, Simdi is a way to get started to express how you want things handled. And so lots of times we think of just making a loop that has independent iterations, but to do optimal work, it's a lot more. It involves having things in the cache, making sure things are aligned, having prefetching available, and then data arrangements, just for instance using SOA instead of AOS, and then masking, whether things are going to be masked or not, and of course striding is the best. So all these other things are involved in there, and sometimes the compilers are being very conservative in what they can vectorize, and you need to tell the compiler what you know and about it, and instruct it that yes, this is a vector loop, go ahead and vectorize it. And for many cases it works fine, but then you get into some cases where it's not, and I'll show you an example. So basically in Silk Plus you have these directives, but we now have them in OpenMP, in OpenMP 4.0 to use these Simdi directives. The nice thing about Silk Plus is that it has C arrays that you can use in C, and that's not available in OpenMP. So there's, but this is very specific to their compiler, and the OpenMP is very generic across different compilers, and this is only for C and C++, whereas OpenMP also favors Fortran. There are some other options there, like IDEV, which is actually a hint, but I want to show you some of those differences. So a little bit of history, OpenMP, Simdi didn't come about until OpenMP 4.0 in 2013. So they were quick to adopt this, and there have been some changes, and not changes, but additions to the 4.5. And basically it's a directive around a loop to say, yes, you can vectorize this, but what's also important is to have a Simdi, to specify the Simdiness of the loop and work with, say, work sharing. And of course you can do that with Silk tasking, and that's powerful, but I think the OpenMP work sharing is even more powerful. And of course you can declare certain functions to be that are elemental, that are basically independent of any of the other variables. You can declare them to be SIMDizable, and basically they could be inlined, and that can be so that you, in a loop, you can have a function and say it's declare it to be a SIMDized function, and the whole loop will be vectorized. You know how function calls in a loop lots of times prevent the compiler from vectorizing a loop. Well, you can specify things about these functions that say no. You can make the vector operations with this function. One of the things is that the compiler lots of times needs help because the pointers may be complicated or the index may be complicated. IDEV is just a hint. This example down here should be able, you look at it carefully and you see that it should be vectorizable. The C version is not. You have to specify with a SIMD pragma, SIMD directive, that yes, it can go ahead and vectorize this, that each of the iterations are independent. Indeed, they are. It says, I command you, this is a demand, I want you to vectorize this loop. I know everything's okay. This actually vectorizes for the Fortran compiler, but not for the C. And what is nice, I think, is that Intel vectorization reports are getting much, much better. It actually says in here for a number 2 report that this could be vectorized. Go look at doing SIMD directives. So it's like, thank you. That's helpful to.
If you use the Intel Advisor tool, in Vector Advisor in the 16.0 release, is very, very helpful at helping you both understand why loops weren't SIMDized, what directives you should put in, and so on, and telling you the degree of efficiency that you're getting from the vectorization.
Yeah.
So certainly go and look at that as well.
So don't listen to this, but if you're working with a different compiler and it's not vectorizing, go over to.
Intel Developer Conference, I can tell you about Intel tools.
Okay. So what's available?
Actually, you're right, but it may not work with those. But the code after you put those SIMD directives in will run with other people's compilers.
Yes. Yes.
So the fact that you chose to use the Intel tool to do the development still gets you ahead on the deal if you go off and run it on some IBM machine or whatever.
Okay. Good. So there are different things that can be done in a loop to make to ensure that you can specify to make sure it's the compiler knows it's vectorizable. These are you can specify that there's a reduction. It'll vectorize that. You can specify the length that you want it, that vector length that you want it to have, or whether variables in there are to be incremented linearly, and then whether it's going to be a private variable or last private. The last time that a certain variable is used, it's going to be accessible. So these are common between the OpenMP and the Silk Plus. Here's an example. This is Fortran, but just change the do for a 4 here, and basically you have it. Where I'm using a reduction, and I have a variable that's incremented by 1, and it will go ahead and vectorize this loop across a 4 wide for, I guess this was double precision. And the things that are different between the two are that the OpenMP, you can state whether it's aligned. Sometimes you can get a big performance boost if the compiler knows it is aligned on that directive. It seems like Intel should have that, I thought, but I'm not sure. And then another thing is you can collapse loops. If you have 2 loops, you can collapse them, where you can't do that on the Silk side. It has first private, but I haven't found the use for that. I think that's a corner case. Vector length 4, you saw over here how I said, well, it's a 4 or 8. I think you can put 4 and 8. I'm really not sure. You might get some help back there. And it will compile versions for vector length 4 and vector length 8. I'm not sure. But what you can do is...
The vector length, sorry, you're talking about Silk. I don't know about Silk. I really don't see much point in us talking about Silk, actually. I mean, this is an OpenMP discussion, and these guys are going to be using OpenMP. So
Okay. Oh, so I'll quickly come to the end then, because I was asked to present silk side versus this, and I was specifically asked that.
I think most of these people are more interested in OpenMP because it's portable and a generic standard than they are in silk.
Okay.
And I can understand that some of our compiler guys who maybe asked to do this said, oh, I did a lot of work on silk, I don't want to lose it. But actually,
Good point. So look over just on the right side, what's available in OpenMP for to do these things. And so you can, OpenMP provides loop collapsing for you, and of course the scheduling. And then we're not going to, what I think is a key feature of the Silk Plus is if you want to use arrays over there, you can. And this
and
specific.
some of this may be coming back in the C standard, right? We're working to get some of this stuff into C standards in various ways into C++ standards. But for what you want to do tomorrow, right, over the next year, whatever it is, you're probably not going to go and rewrite the stuff in Silk, even though Silk syntax is supported by GCC and whatever all else. Because it isn't as portable as being something like OpenMP that has commitment for support for everything. And also, it isn't in Fortran.
Okay, some of my key points. Thank you for the summary. Let me get to the end. So what is nice, well, I'll just skip those. And then, so what about using the declaration? So on functions, you can declare how they're to be used, the Simdi length, whether variables are linear, whether they're uniform, whether there's branching or not, and that can help the compiler optimize that, and in particular where it's lined. And we've seen at TACC lots of codes that if you could tell them that it's going to be lined, that could get you 20%. And with that, no more silk. We'll go right to the end. Simdi. There's no C arrays, but you're limited to C over here. And C++, we have Fortran working on this side. You can work with work sharing just like you can do over here. And then you specify the functions, how they're to be SIMDized. There's no prefetching, but soon we feel that will come in the standard. People are talking about doing that kind of thing. And onward to 5.0. Some of the things people are talking about is doing, let's see, these are just some of the summary points that you provided. We can skip that because it's getting close to lunch. Here are the futures, doing NUMA memory control, whether you used high-speed memory or not, interoperability with the Silk. And then we have do across, we have task loops, things like that that are, well, we're using task loops now, but we have do across in 4.5, and they want to talk about extending that to other types of doing pipelining across several loops, and so that's going to be good. Using fat and thin cores on a single processor. And how to do that, we're looking at that right now. So that's the future. I hope I've exposed enough of the new things in OpenMP for the Intel compiler, and I appreciate the aggressiveness Intel has shown us in adopting these things. So thank you very much.
So
Okay.